Assalamualaikum warahmatullahi wabarakatuh. So now we are going to continue with chapter 3 for physics sem 2, electric current and DC circuits. So in this chapter we are only learning the first four first. Okay, so we have 3.1, 0.2, 0.3 and 0.4. And this is the equations, 6 equations that we are going to learn in this first 4 subtopics. Okay, so without wasting any time, we are looking at the introduction video about 3.1 electrical conduction. So 3.1 3.1.1 electric current. So electric current you have learned in school before. The unit is ampere or the symbol is A. So let's say we have a simple circuit with battery and bulb and a wire in the circuit, the simplest closed circuit that we can have. So there's two directions that you need to consider. The first one is the electric field or electric current. It was flow from positive terminal to negative terminal, and we have electrons flow, and electrons flow from negative to positive terminal. Because electron itself is negatively charged, so they move from negative to positive terminal. It was opposite with the electric field direction, electric current direction. And the equations for current is I is equal to charge over time, and this is an instantaneous current. For electrical conduction in metal, so in metal, the charge carrier is free electrons, and a lot of free electrons are available in it. So every metals we have free electron inside, and it moves freely and randomly, like in this figure. So this free electrons move at any direction randomly, and when we switch on the circuits or electric field is applied to the metal, these free electrons in this wire will experience electric force, and all the electrons inside the wire will drift with constant average velocity towards the opposite direction of the field, like this. Okay, so let's say our electric field move from left to right. This is our electron. Firstly, it moves randomly, but when we apply electric field, it will flow from negative to positive terminal. Okay, you must remember that electric field or electric current is opposite direction flow from electron flow. Electron flow negative to positive, electric field positive to negative. This is also the same direction as the electric field. This is I is electric current. Electric current is flowing in the opposite direction of the electron flows. So for example 3.1, a silver wire carries a current of 3 ampere. So we have our I is 3. Questions A, determine the number of electrons per second pass through the wire. So the questions A1 N over T. So I is equal to Q over T. We only have one equations in this subtopic. So we know that Q is equal to NE, number of electron times charge of electrons. So we just substituting in the equations. So yeah, we have I, and then E is electron charge is a constant value they give you in the questions. Yeah. So we want the N over T. So do your maths, and then you will get 1.88 times 10 to the power of 19 electrons per second. So for questions B, the amount of charge flows through a cross-sectional area of the wire in 55 seconds. So we have the 55 seconds. They want the amount of charge flow. That's mean we want the Q. So we know that Q is equal to IT. So we have the I, which is 3, and then T is 55. So just press the calculator and you will get 165. And don't forget that the unit for charge is coulomb. You have learned in chapter 1. So next is 3.2, resistivity and Ohm's law. We will look a video first before we proceeding. Right, 3.2 resistivity and Ohm's law. Okay, first we cover resistance R first, yeah. So resistance is the, okay, this is to make it simple. R resistance is equal to V over I, where V is the potential difference voltage and I is the current. We learned current just now. So resistance is the measure of components' opposition to the flow of electric charge. And it was scalar and the unit is ohm. We all voltage over ampere. You have learned this in school. So just be very quick. And in general, the resistance of a metallic conductor increases with temperature. Okay, so if we have a simple circuit, when we let it be for a long time, the circuit, the wire or the bulb will produce heat. Okay, so when the temperature increase, the resistance of the metal wire will be increased as well. But if the temperature of the metallic conductor or wire is constant, hence its resistance also constant. Okay, just now we learned about resistance. Now it was different. It was resistivity. It's two different things. And the symbol is rho. Just now resistance is R and resistivity is rho this time. Okay, what is resistivity? So resistivity is R A over L. So R is resistance, A is cross-sectional area, and L is the length of the material. It was a scalar quantity. So when we derive from the equations from the formula, the units of resistivity is ohm meter, because R is ohm and then area over length is length. So you will get ohm meter. And resistivity is a measure of a material's ability to oppose the flow of an electric current. And resistivity depends on the type of material and temperature. So please remember that resistance just now only depend on the temperature, but resistivity, it depends on the temperature and the type of material made from the wire. So for example, copper wire have different resistivity. What else? Lead wire will produce different resistivity. Okay, and a good electric conductors have a very low resistivities, and good insulator have a very high resistivity. Right. So an example for 3.2, a wire of length 10 meter, which is L, and diameter of 4 millimeter has an electrical conductivity of 6 times 10 to the power 7 per ohm per meter. Calculate the resistivity of the wire. So make sure you know, if you look at the questions, they ask resistivity and then B resistance. So A they want the rho and then B they want the R. So electrical conductivity, the formula is 1 over rho, because if we look at the unit here is the unit here, we know that resistivity is ohm meter, so the unit given is per ohm per meter. So we can get the equations for electric conductivity, which is 1 over rho. Okay, and then we get the what you call sigma, the sigma already, which is 6 times 10 to the power 7, and then we get the resistivity. Okay, that was a very simple task. Okay, now calculate the resistance of the wire. So we have the resistivity from A, so we just want to calculate the R. We arrange from the equation rho L over A. So we have the rho from A, and then L is 10, and then area is pi R square, but if we derive in the diameter term, you can get pi d square over 4, and then we rearrange and then we substitute. Okay, and the rho is 1.67 times 10 to the power 8, length is 10 meter, and then we have the diameter. If you want to find the radius from diameter, also can. you will yield the same answer, right? So yeah, this is your answer. Next is Ohm's law. So Ohm's law state that our potential difference V is directly proportional to current. Okay, so V is equal to IR. Okay, so R is constant there. So V is potential difference, I is current, R is resistance. So we have V is equal to IR. So when we do experiment and we varies the value of V or I, so we get this graph, and then the graph will show that V is directly proportional to I, where the gradient of the graph is our R resistance. So you know how to get the gradient from the graph. Yeah? This is a very simple thing. Right. So a wire of length 50 meters, so that was L. A current 10 ampere, so that was I. The potential difference across both ends of the wire is 2.1, so that was V. Determine the electric field intensity. So we have learned V is equal to EL or V is equal to ED in chapter 1, electrostatic. So we just substitute all the values that we have, and then we get the E. And then for B, the resistance of the wire. So we have the V is equal to IR, Ohm's law. We have the V, and then we have the current as well. So we want to find resistance. We just substitute and rearrange. We get 0.21 ohm. And then 3.3, the variation of resistance with temperature. Now we have two things that we need to consider. So the first one is metal. So when the metal increases, the number of free electrons per unit volume of metal remain unchanged. Metal atoms in the crystal lattice vibrate with greater amplitude and cause the number of collisions between the free electrons and metal atom increases. Hence, the resistance in the metal increases. I think I've told you before that the resistance only depends on the temperature. So when they need the or when you are curious about the explanation, this is what I'm talking about. Yeah. So we have a lot of free electrons in the copper wire. In the wire, doesn't matter if it's any metal. Okay, let's say we have a wire. So in wire have a lot of free electrons, and when it was heated, the collision among the free electrons will be very, very higher, and then the number of collision increases, hence the resistance of the metal increases. So if we have a superconductor is a class of metals and compound whose resistance decreases to 0 when they are below the critical temperature. And we have a new parameter, which is alpha. Alpha is coefficient of resistivity. It was a fractional increases in resistivity of a conductor per unit rise in temperature. So mathematically, alpha is equal to delta rho over rho naught delta T, where delta rho is change in resistivity, change in temperature for delta T, and initial resistivity for rho naught. So when we rearrange this, you get these equations, and since rho is directly proportional to resistance, so we can just substitute rho with R, and the unit for alpha is per degree Celsius or per Kelvin. If you notice that these equations is a little bit the same, no, a little bit, it was exactly the same like the equations that we learned in chapter 12 in Sem 1, where length is equal to length naught 1 over alpha delta T. Okay, so from these equations, the resistivity of a conductor varies approximately linearly with temperature. So when temperature increases, resistivity also increases. Now, a copper wire has a resistance of 25 milliohm. Resistance, not resistivity. So this is R of 25 milliohm. Don't forget the prefix. At 20 degrees Celsius, when the wire is carrying a current, heat produced by the current causes the temperature of the wire to increase by, not to. It was increased by 27. That means the initial temperature you need to plus with 27 to get the final temperature. So calculate the change in wire resistance. They want the delta R. So we list all the information that we can get. So we are using this because we want to find the resistance. If they ask you resistivity, then we use the resistivity equations. So we arrange. And then then when we have finished rearrange, we just substitute the value. So do your maths and then you get 4.6 times 10 to the power of negative 3 milli. Oh, sorry, 4.6 times 10 to the power of negative 3 ohms. I want to say milli ohm. Okay. So you get what I mean, yeah? Right. The last one, 3.4. Electromotive force, EMF, potential difference, and internal resistance. Okay. So EMF, what you call? Epsilon, and potential difference V. So let's say we have this circuit. We have the battery, we have wire, and then we have resistance. Okay. So right, what is EMF? Okay, is an EMF or electromotive force is defined as the energy provided by the source or battery to each unit charge that flows through the external and internal resistance. So in the battery, the original energy provided is called the EMF. Okay, right. Meanwhile, for terminal velocity or terminal potential difference is the work done in bringing a unit test charge from the negative to positive terminal of the battery through external resistance only. Right, so this is how the equations will be. So V is potential difference or voltage is equal to EMF minus current times internal resistance. Small r is the internal resistance, big R is the external resistance. So if we look again at our previous figure, so we have two types of R. So the big R for the external resistance, for small r is the internal resistance. Internal resistance is the resistance inside the battery, inside the cell. So they live together, the EMF and the internal resistance. So when we rearrange this, okay, we derive the V is equal to IR from Ohm's law. And then when we rearrange this, we get the final equations for the EMF in terms of R, capital R and small r. So the unit for both is volt. So if the battery for the battery without internal resistance, or if there's no current flow in the circuit, then V is directly equal to EMF. Right, internal resistance of a battery. So internal resistance is the resistance of the chemicals inside the cell between the poles. So the equations to find the internal resistance is voltage R potential difference across internal resistors over the current in the circuit. And the value of internal resistance varies because it was depend on the type of chemical materials inside the battery. Okay, there is a symbol for EMF and internal resistance. I have told you before, so it can be right or it can be left, doesn't matter. Right, a battery has an EMF of 9 volt and internal resistance, small r, 6 ohm. Determine the potential difference across its terminal when it is supplying a current of 0.5 ampere. Okay, so they want the potential difference, so they want the V. Yeah? So we have the EMF, we have the current, we have the R, so we just substitute and then you get the V, 6 volt. And for B, determine the maximum current which the battery could supply. So the current is maximum when the total external resistance R is 0. So use these equations again and then you substitute again. Okay, and then you get current. Why the current is maximum when the total external resistance R equal to 0? Because if we imagine that in our circuit, when there is no resistance, then the current will be very, very high. The bulb will be very, very bright. Compared to a circuit with a very high resistance, the bulb will produce a very low light compared to a lower resistance circuit. Okay, that's it for the first 4. See you later. Have a nice day, guys.